Most times, the sampling distribution of the means will have more than 10 values, as in our first example, and it becomes impossible to put the data in a calculator to find the standard error. Okay, so we calculated our standard error by first finding out what all the possible samples of size 2 were, and then finding each of those sample means, and then putting each of those sample means into the calculator, and then running one of our stats to find out what the standard deviation was for that collection of sample means. When that collection of sample means becomes too big, and it will become very big very fast, it's impossible to put all the data in the calculator just to find the standard error. So in that case, we use a formula. If we know the population standard deviation, which is sigma, and we know the sample size that was used to create the sampling distribution, the following formula will give us the standard error. We simply take the population standard deviation and divide by the square root of the sample size. Using symbols, we have sigma x bar equals sigma, the population standard deviation, divided by the square root of n, which is the square root of the sample size. So your standard error is equal to the population standard deviation divided by the square root of the sample size. So let's see if that formula for the standard error will produce the same standard error that we got when we put it in the calculator. Because I said that when the calculator list becomes too large, it's not feasible to put all those values into a list. So let's see if we can recreate this number using our formula. So from before, we calculated the population standard deviation of those 5 data values to be 30.2787. Those were the 5 commuters. We put them in a list. We calculated the population standard deviation at 30.2787. The sample size, which was the sample that was used to create the sampling distribution, is 2. So n is 2. So if we put this in a formula, 30.2787 divided by square root of 2, and I don't know if we've seen the square root key on our calculator yet. See, 30.2787. Okay, so 30.2787 divided by square root. If you haven't seen it before, it's here in blue. It's above the x squared key. So you're going to do second square root, and you're going to put 2 because that's the sample size. Okay, then you're going to hit enter, and you're going to get a value. This is the result of our formula, 21.4103. I'm going to round standard deviations and standard errors always to 4 places. So 21.4103, which is not the 18.5418 that we got before. When we put it in our calculator and we calculated the standard deviation of the sample means, we got 18.5418. When we use the formula, we have 21.4103. So why is there a discrepancy in our answer if this formula is supposed to produce the same number? Okay, so the reason why is because our sample of size 2 relative to the size of the population of size 5 is very large. So if we take our sample size 2 and we divide it by 5, we see that that proportion is 40%, basically 0.4 or 40%. When that happens, when we have a large sample to population ratio, we have to apply this factor called the finite correction factor. For samples too large relative to the population, there's an additional piece to the formula for the standard error called the finite correction factor. And the rule is too large means n divided by n, which is in this case 2 divided by 5, or whatever sample size divided by whatever population size. If n divided by n is greater than 5%, then we add this piece to the standard error formula. We have the same formula as before, sigma divided by the square root of n, and then we multiply by this piece called the finite correction factor. The square root of capital N minus n over capital N minus 1. Now, in our case, 2 divided by 5 is 40%, which is greater than 5%, so we have to apply the finite correction factor. So let's see if that works. So, as before, we have our sigma 30.2787 divided by our square root of n, square root of 2. But with the finite correction factor, we're going to multiply by the square root of capital N minus n, which is 5 minus 2 over 5 minus 1. That becomes the square root of 3 over 4. Square root of 3 over 4. So let's go to the calculator and demonstrate that it will work. So we have 30.2787 divided by the square root of 2. Now, notice that my cursor is underneath the square root symbol. Before I write the next symbol, which is multiplication, I have to move the cursor out. So what I'm going to do is press my arrow to the right. And now notice that my cursor is flashing outside of the square root symbol. So I could now write times, and the next thing that we're multiplying by is the square root of 3 over 4. So second square root 3 divided by 4. Okay, so that's the end. Simply the finite correction factor is just this last piece here where we multiply by the square root of 3 divided by 4. And then we hit enter. And notice what happens. We have a value that's identical, 18.5418, to what we had earlier for the standard error. So when needed, you have to use the finite correction factor. Okay, you will be required to use the finite correction factor on your graded homework. Okay, so there is a WebWork homework associated with this particular lecture, and you will need to use the finite correction factor on that homework. However, for the remainder of this lecture, and for questions that do not direct you to use the finite correction factor, you will not need to use it. So you'll need to do it once for that homework assignment, but in the future, on the multiple choice questions on the final exam, or on any practice questions that you do for homework or for test practice, you will not need to use the finite correction factor. So it's the formula for the standard error is simply sigma divided by square root of n, and that will be it. So to find the standard error for most problems, sigma divided by the square root of n, and then the standard error is denoted by sigma subscript x bar. Okay, so WebWork homework 12, you're going to need to apply the finite correction factor. There's very few problems from the textbook that require you to do this, but if you're doing it for practice, just take note of the need for the finite correction factor when the problem calls for it.